doing better than numpy's in1d mask function, ordered arrays. This operation needs to be applied as fast as possible as the actual arrays, which contain millions of elements. This is a simple version of the problem. So, I have a random array of unique integers, normally millions of elements. Totalids equals 5, 4, 3, 1, 2, 9, 7, 6, 8. I have another array, normally a tens of thousands of unique integers, which I can create a mask. I can use numpy to do mask equals np.in1d totalids, subsamplelids, assume underscore unique equals true. I can then extract the information I want of another array using the mask, say column 0 contains the one I want. Variable equals or variables mask, 0. Now, given that the ids are unique in both arrays, is there any way to speed this up significantly? It takes a long time to construct the mask for a few thousand points, subsamplelids, matching against millions of ids, totalids. I thought of going through it once and writing out a binary file of an index, to speed up future searches. Where X is in subsample IDs. Then I can just do right. But this is also slow because there is a conditional in the loop to find when it first matches. Is there a faster way to find when a number first appears in an ordered array so the conditional doesn't slow the loop?
I suggest you use data frame in pandas. The index of the data frame is the totalids, and you can select subsamplelids by df.9 subsamplelids. Create some test data first. Then convert your data into a data frame. Data frame use a hash table to map the index to its location. It's very fast.
Often this kind of indexing is best performed using a DB, with proper column indexing. Another idea is to sort totalids once, as a pre-processing stage, and implement your own version of in1d, which avoids sorting everything. The numpy implementation of in1d, at least in the version that I have installed, is fairly simple, and should be easy to copy and modify. Edit. Or, even better, use bucket sort, or radix sort. That should give you O(n plus m), n being the size of totalids, and in the size of samplelids, times a constant you can play with by changing the number of buckets. Here too, you can split totalids to buckets only once, which gives you a nifty O(n plus m1 plus m2 plus. Unfortunately, I'm not aware of a numpy implementation, but I did find this URL.